A quadratic expression has the form ax squared plus bx plus c. A cannot equal 0, because if a was equal to 0, we would have no x squared term. In that case, we don't have a quadratic, we might have a linear expression if b is not 0. Now in this section I will be dealing with quadratic expressions that have real coefficients. The graph of the function y equals ax squared plus bx plus c is a parabola. Now I've shown an upright parabola, but it might be upside down. It will be upside down if a is negative. But we don't have to worry about that situation, because everything I'm saying here will also apply for the situation where a is negative. What I'm showing here are situations for when a is positive. So we'll have an upright parabola. Now if we look at the quadratic equation ax squared plus bx plus c equals 0, we know that the solutions are given by minus b plus or minus the square root of b squared minus 4ac all over 2a. Now the plus or minus indicates that there are two values of x that satisfy this equation. Those two values of x are denoted by the letters alpha and beta. Now it doesn't matter which one you call alpha and which one you call beta. I'm calling alpha the value of x that has the minus sign in front of the square root, and beta is the one with the plus sign, but it doesn't matter. Now if b squared minus 4ac is some positive number, some number greater than 0, then we will have two distinct values for our solutions. Alpha will be different from beta. For alpha we'll subtract this quantity, for beta we will be adding this quantity. So we'll get two different roots or solutions. And these two distinct roots are the x values on the curve for which y is equal to 0. See, we have y equal to 0 here. So these will be the values where the curve crosses the x-axis. Now what happens when b squared minus 4ac is equal to 0? Well, we don't have any, this term just disappears. So we don't have this term. So it doesn't matter about taking minus 0 or plus 0. We'll find that alpha is equal to beta, and alpha is minus b over 2a. So this will be the solution. So the graph will only cross the x-axis at one point. So there's only one point on the graph for which y is equal to 0. We can call it alpha, but we know that it's given by minus b over 2a. So I could write minus b over 2a here. Now of course this is not necessarily negative. Like, just because we have a minus sign here, I mean b could be negative, so, and a could be positive, so you know this could be a positive quantity, so it's okay to show this in this quadrant. As a matter of fact, minus b over 2a is a point that's midway between alpha and beta for this situation. If you just add these two together and divide by 2, the square root parts will disappear and you will be left with minus b over 2a, which is midway between alpha and beta. It's actually on the axis of symmetry of the curve. Finally, what happens if b squared minus 4ac is less than 0? In other words, if b squared minus 4ac is negative, we will be getting the square root of a negative number. So like, say b squared minus 4a is minus 16. That's not a real number. It can be written as a complex number. It's the complex number 4i. So that's in the complex numbers section. So if you haven't seen complex numbers before, it doesn't really matter. But we won't be talking about them here. We say that we have complex solutions to our quadratic equations. But that means that the graph doesn't cross the x-axis. So there are no real solutions. Now in this section I want to discuss the relationship between the roots alpha and beta of a quadratic equation and the coefficients a, b and c. So alpha and beta are the roots of ax squared plus bx plus c equals 0. Of course a can't be 0. By the factor theorem, which is covered in an earlier video, since alpha is a root, it means that x minus alpha is a factor of this quadratic expression. beta is a root, which means that x minus beta is a factor of this quadratic expression. Now, since we're talking about a quadratic equation, there are at most two distinct roots, which means that there are just two factors. And if we multiply these two factors together, we will actually get this quadratic. So if we multiply x minus alpha by x minus beta, we will actually get this quadratic expression. However, we just have to add in another factor of a. Well, a is just a number. When I say there are only two factors, I mean there's only two linear factors. Two linear factors involve x to the power of 1. And when we multiply the two linear factors together, we get this quadratic expression. We get an x squared term for multiplying x by x. But we want ax squared. A is not necessarily 1. So we need to stick in an a here. So what we can do now is compare both sides and get the relationship between alpha and beta, which are the roots, and a, b, and c, which are the coefficients of this quadratic expression. So to be able to match up both sides easily, we can divide both sides by a. So if we divide this right hand side by a, we get x squared plus b over ax plus c over a. Of course, we're allowed to divide by a because a is not 0. Then we just multiply this out. We get x squared minus beta x minus alpha x. That gives the term minus bracket alpha plus beta x. Okay, we get a minus beta x and a minus alpha x, and we can combine those into minus bracket alpha plus beta x. The constant term is minus alpha by minus beta, which is plus alpha beta. And it must equal this here. Now this equation that we have here is called an identity. An identity is an equation that is true for all values of x. Not just true for some values, but true for all values. That's what an identity is. Alpha and beta are constants, they're fixed values. So the only way that this thing can be true for all values of x is if the coefficients of x on both sides are the same, and if the constant terms on both sides are the same. We don't have to worry about x squareds. The coefficients of the x squared terms are 1. So the x squared terms are equal. So you see, it doesn't matter what value we put in for x. If the coefficients of x and the constant terms are the same, then both sides will be identical for all values of x. So equating the coefficients of x, we get minus into alpha plus beta equals b over a. And we can write that as alpha plus beta equals minus b over a. We just change signs on both sides. So here is one important relation. It says that the sum of the roots of a quadratic equation is given by minus b over a. If we equate the constant terms, that is the terms that don't contain x, we see that the product of the roots, alpha and beta, is given by c over a. Now here is an example based on what we just did. If alpha and beta are the roots of the quadratic equation 3x squared minus 5x plus 7 equals 0, find alpha plus beta, alpha squared plus beta squared, alpha cubed plus beta cubed, and 1 over alpha plus 1 over beta. So we need the relationship between the roots, alpha and beta, and the coefficients a, b, and c. We know that the sum of the roots is given by minus b over a. So what is minus b over a for this equation? Well, b is the coefficient of x, which is minus 5. A is the coefficient of x squared, which is 3. So we see that alpha plus beta is 5/3. Alpha beta is given by c over a. So that means that we can put 7 over 3 to get the product of the roots. So we don't have to actually find the roots. So these are our two key formulas. Now, we have to get alpha squared plus beta squared. And we can do this without finding alpha and beta. I mean, we could find alpha and beta just by solving between these two equations, or just simply getting the roots of this equation. But we don't need to do that, because we can use an identity to get alpha squared plus beta squared. It's an identity that involves alpha plus beta and alpha beta. We can write this as alpha plus beta squared minus 2 alpha beta. And you see we have alpha plus beta, it's 5/3, and we have alpha beta, that's 7/3. Now it's easy to check that this is true. We just expand this out, we get alpha squared plus 2 alpha beta plus beta squared, and we subtract the 2 alpha beta. So you can see that these terms cancel out and we're left with alpha squared plus beta squared. So this identity is true. Plugging in for alpha plus beta and alpha beta, we get 5/3 squared minus 2 times 7/3. 5/3 times 5/3 is 25/9. Minus 2 by 7/3 is minus 14/3. That can be written as minus 42/9. So we get 25 minus 42, which is minus 17. So we get minus 17/9. Now, what about alpha cubed plus beta cubed? Well, we can factorize this thing into alpha plus beta times alpha squared minus alpha beta plus beta squared. If you multiply this out, you can check it. Everything will break down to alpha cubed plus beta cubed. This identity is sometimes called a sum of two cubes. We know what alpha plus beta is. That's the sum of the roots. It's minus b over a, which is 5/3. And inside here we have alpha squared plus beta squared, but we've already calculated that. It's minus 17/9. We also have alpha beta. Alpha beta is 7/3. To two decimal places we get minus 7.04. Now, in case you're wondering, you might have noticed that this number here is alpha squared plus beta squared, but it's negative. How is that? If you take any real number and square it, we get a positive number. Same is true for beta, of course. So we have the sum of two positive numbers giving us a negative number. What's going on there? Well, the only way that can explain this situation is that alpha and beta are complex numbers. And I won't say much more about this. This is for another section. So, in other words, this equation cannot have real solutions, because if it had, alpha squared plus beta squared would be a positive number. Finally, let's look at 1 over alpha plus 1 over beta. We can add these two fractions to get this single fraction. Just multiply the denominators together to get alpha beta. Divide alpha into alpha beta to get beta. Beta times 1 is beta. Divide beta into alpha beta to get alpha. Alpha times 1 is alpha. So you can see that on top we have the sum of the two roots, which is minus b over a, which is 5/3. And underneath we have the product of the roots, which is 7/3. 5/3 divided by 7/3 is 5/7. So you see we can work out all of these without knowing what the roots alpha and beta are. Now in this section we're going to discuss forming quadratic equations from the two roots. So a lot of this you've seen already. If alpha and beta are the roots of a quadratic equation, then the quadratic equation is given by x minus alpha times x minus beta equals 0. And if we multiply this out, we get x squared minus alpha plus beta times x plus alpha beta equals 0. It's useful to think of this in words. This is x squared minus the sum of the roots times x plus the product of the roots equals 0. Now you might say, but the coefficient of x squared is 1. So what if we have an equation like this? Say 2x squared minus 3x plus 4 equals 0. Well, it's not given by this because the coefficient of x squared is 1. Well, all you've got to do is just divide across by 2. And then we have x squared minus 3 over 2x plus 4 divided by 2 is 2 equals 0 divided by 2 is 0. So we can always divide across by a. A is never 0, of course. So these two equations are identical. So if you have something in front of x squared that's not 1, you just divide across by it, and this form here can be got from this here, by getting x squared minus the sum of the roots times x plus the product of the roots equals 0. Now here's an example that uses those ideas. If alpha and beta are the roots of x squared minus x minus 4 equals 0, form an equation with roots 2 alpha minus 1 and 2 beta minus 1. Now, let's form that equation. We know that such an equation is given by x squared minus the sum of the roots times x plus the product of the roots equals 0. So let's get the sum of the roots. So we just add these two together. What will that give us? It'll give us 2 alpha plus 2 beta minus 2. So that's just summing the two roots. And then we multiply the two roots together. So here's our equation. So this is an equation whose roots are 2 alpha minus 1 and 2 beta minus 1. Now we can write what's in here like this. We can factorize 2 out of alpha and beta. So we have alpha plus beta in here. Multiplying this out, 2 alpha by 2 beta is 4 alpha beta. We get a minus 2 alpha and a minus 2 beta. Minus 2 alpha minus 2 beta can be written like this. We can factorize out the minus 2. Minus 1 by minus 1 is plus 1. Now we know something about alpha and beta. We know that alpha and beta are the roots of this equation here. We know that alpha plus beta, that's the sum of the roots of this equation, is given by minus b over a, where b is minus 1 and a is plus 1. So we have minus minus 1 over a. That's going to give us plus 1 over 1, or 1. And we know that the product of the roots is given by c over a. So these are our two key formulas. So the product of the roots of this equation are minus 4 over 1, which is minus 4. So now we can sub in those values and we'll get an equation whose roots are 2 alpha minus 1 and 2 beta minus 1. So we can do that without actually finding what alpha and beta are. If we simplify this down here, we have 2 minus 2 is 0, 0x. And if we simplify this here, we get minus 16, minus 2 is minus 18, plus 1 is minus 17. So the constant term is minus 17. 0x is 0. So here is our quadratic equation. Now I wasn't expecting the x term to be 0, but because it is 0, we can actually quickly solve this equation if we want to. We could just get the square root of 17.